The moment arrived without fanfare or cosmic announcement. On September 15th, 2025, 3I Atlas crossed an invisible threshold in space that changed everything. The interstellar visitor, already the subject of intense scientific scrutiny for its anomalous mass and bizarre chemistry, had reached the point where solar gravity became inescapable. There would be no turning back now. The object was committed to its plunge toward the Sun. In orbital mechanics, this threshold carries a specific meaning that differs from casual understanding. 3I Atlas follows a hyperbolic trajectory, meaning it possesses more than enough velocity to eventually escape the solar system entirely. But at this particular moment, having travelled inward from the cold outer reaches where it first appeared, the object entered a phase where its path curves most sharply around our star. Every second now brings it closer to perihelion, the point of nearest approach, with velocity increasing under the relentless pull of solar gravity. Astronomers tracking the visitor from observatories scattered across 6 continents recognized the significance immediately. Pre-perihelion observations, already difficult as the object moved closer to the Sun in Earth's sky, would soon become impossible. The geometry of the solar system was conspiring against them. 3I Atlas approaches perihelion on the far side of the Sun from Earth's perspective, meaning the very moment when solar heating reaches maximum intensity, when outgassing explodes to peak levels, when the object's true nature might finally reveal itself through extreme stress, humanity's telescopes would be completely blind. The countdown had begun in earnest. Roughly 90 days separated this threshold crossing from perihelion passage itself. 90 days to capture every possible measurement, every spectral signature, every morphological change as increasing solar radiation transformed the visitor. After that would come months of observational darkness, a blackout period when the Sun's overwhelming glare would hide 3I Atlas from Earth-based instruments entirely. What made this threshold crossing particularly urgent was the accumulating mystery surrounding the object itself. The preliminary mass estimates suggesting a 33 billion ton giant. The inexplicable absence of measurable rocket acceleration despite visible outgassing. The nickel emissions without corresponding iron. The carbon dioxide rich chemistry indicating formation in frigid alien environments. The persistent anti-tail pointing toward the Sun rather than away from it. Every anomaly raised questions that perihelion passage might answer, if only astronomers could observe it. But they could not. The geometry was fixed, determined by the object's trajectory and Earth's orbital position. 3I Atlas would make its closest approach to the Sun while hidden behind our star's blinding photosphere. The supreme irony struck every researcher working on the project. After months of careful observation, building the most comprehensive data set ever compiled for an interstellar visitor, the most critical phase would unfold in darkness. The point of no return had been crossed. Now came the race to capture everything possible before the blackout descended. The numbers told a story of accelerating destiny. 3I Atlas was falling toward the Sun at speeds that increased with every passing hour. Current velocity measurements placed the object at approximately 40 kilometers per second relative to our star. But this figure represented merely a snapshot of a constantly changing situation. As solar gravity pulled harder, the visitor would accelerate to nearly 70 kilometers per second by the time it reached perihelion. To understand what this meant, required converting abstract numbers into tangible timeframes. At current position and velocity, 3I Atlas sat roughly 1.2 astronomical units from the Sun, about 113 million kilometers of remaining distance. The closest approach would occur at approximately 0.39 astronomical units, bringing it within 58 million kilometers of the solar surface. This placed the visitor well inside Mercury's orbit, subjecting it to thermal conditions no interstellar object had ever experienced under human observation. The countdown clock displayed at observatories worldwide showed 87 days until perihelion passage. 87 days translated to 2,088 hours, 125,280 minutes, or 7,516,800 seconds. Each tick brought measurable changes. Solar flux increased following an inverse square law, meaning that as distance halved, heating intensity quadrupled. The physics was relentless and perfectly predictable. What remained unpredictable was how 3I Atlas would respond to this thermal assault. Comets typically brightened dramatically as they approached the Sun, their activity increasing exponentially as volatile ices sublimated at accelerating rates. Water ice became active around 3 astronomical units from the Sun. Carbon dioxide, which 3I Atlas possessed in unusual abundance, activated much farther out, where temperatures barely reached minus 125 degrees Celsius. By perihelion, surface temperatures would soar above several hundred degrees, potentially triggering sublimation of compounds that remained frozen throughout most of the solar system. The observation window was closing like a slowly descending curtain. Currently, 3I Atlas remained visible in Earth's morning sky before sunrise, a faint smudge requiring substantial telescope aperture to detect against the brightening dawn. Each day, it crept closer to the Sun's position in the sky, making observations increasingly difficult as solar glare overwhelmed the dim comet. Within 30 days, it would pass through Superior Conjunction, moving behind the Sun from Earth's perspective and vanishing completely from terrestrial observatories. This created an urgent asymmetry in the observation campaign. Astronomers possessed roughly 1 month to capture pre-perihelion data at close solar distances, then would endure approximately 4 months of complete observational blackout before the object emerged on the Sun's opposite side for post-perihelion analysis. Everything depended on maximizing data collection during this final window. The countdown clock kept ticking, indifferent to human curiosity or scientific urgency. Perihelion was coming whether humanity was ready or not. The geometry of the solar system was about to impose a cruel limitation on human curiosity. 3I Atlas would reach its moment of greatest activity, its period of maximum transformation under intense solar heating, at precisely the time when Earth-based telescopes could not observe it. This was not a failure of technology or planning. It was simple orbital mechanics, creating an observational gap that no amount of ingenuity could overcome from our planet's surface. The problem began with Earth's position relative to the visitor's trajectory. 3I Atlas approaches perihelion on December 26, 2025, at a point in its orbit that places it on the far side of the Sun as seen from Earth. Our star, with an angular diameter of roughly half a degree in the sky, would completely block any view of the interstellar visitor during its closest approach. But the obstruction extended far beyond the Sun's visible disk. Solar glare created an exclusion zone spanning approximately 30 degrees on either side of the Sun's position. Any object within this region became effectively invisible to ground-based telescopes, drowned out by scattered sunlight in Earth's atmosphere, and overwhelmed by the star's billion-fold brightness advantage. This meant the observational blackout would not last mere days, but stretch across months as 3I Atlas travelled through this forbidden zone. The timeline painted a frustrating picture. Superior conjunction, when the object passed directly behind the Sun from Earth's viewpoint, would occur in late November 2025. At that point, all direct observation from our planet would cease. The visitor would remain hidden until late March or early April 2026, when it finally emerged on the Sun's opposite side at sufficient angular separation for recovery observations. 4 full months of darkness, bracketing the most scientifically valuable period of the entire passage. What made this blackout particularly agonizing was the list of questions that perihelion passage should answer. Would the object fragment under thermal stress, revealing internal structure? Would outgassing rates surge to levels that finally produced measurable non-gravitational acceleration, testing the controversial mass estimates? Would dormant volatile species activate, exposing new layers of chemical complexity? Would the mysterious anti-tail and sunward glow transform or disappear entirely? Would any unexpected trajectory changes occur that might distinguish between natural comet physics and more exotic explanations? Every one of these questions required continuous observation through perihelion to answer definitively. Instead, astronomers would capture pre-perihelion data while the object remained relatively cool and distant, then wait months before seeing post-perihelion conditions after peak heating had already passed. The critical transition period, the actual passage through maximum solar flux, would occur in complete observational darkness from Earth. It was like watching someone walk toward a door, having them disappear as they passed through it, then seeing them emerge on the other side, having potentially undergone complete transformation. Whatever happened in between would remain forever unknown unless other observers, positioned elsewhere in the solar system, could witness what Earth could not. Solar radiation was transforming 3I Atlas in real time. As the interstellar visitor plunged deeper into the inner solar system, the increasing flux of sunlight triggered cascading physical changes across its surface. What began as a relatively dormant object displaying modest activity levels was awakening into something far more dynamic and spectacular. The physics driving this transformation followed well-understood principles. Solar heating penetrates the outer layers of cometary material, raising temperatures until volatile ices reach their sublimation points. Different compounds vaporize at different temperatures, creating a sequential activation pattern as the object warmed. Carbon dioxide, already active since the visitor's discovery far beyond Mars' orbit, now sublimated at accelerating rates. Water ice, dormant during the outer solar system passage, began contributing substantially to gas production as surface temperatures climbed above freezing. Recent photometric measurements documented dramatic brightening consistent with this thermal awakening. Observations from late September 2025 showed the object had increased in brightness by nearly 2 magnitudes compared to measurements from July when discovery first occurred. This 100-fold increase in visible light output reflected both enhanced dust production and expanding gas emissions, as sublimation rates surged under intensifying solar heating. The coma, that diffuse cloud of gas and dust surrounding the solid nucleus, had grown substantially. Early imaging revealed a relatively compact envelope extending perhaps 50,000 kilometers from the central condensation. Current observations showed the coma spanning several 100,000 kilometers, with the carbon dioxide envelope detected by infrared telescopes reaching even greater dimensions. This expanding atmosphere represented millions of kilograms of material escaping from the nucleus every day, possibly accelerating toward hundreds of kilograms per second as perihelion approached. Spectroscopic monitoring revealed the chemical complexity of this awakening. Water vapor lines strengthened dramatically in recent weeks, joining the carbon dioxide and carbon monoxide signatures detected since August. More exotic species appeared in the spectra as well. Ammonia, methane, and various organic compounds contributed their characteristic emission features as temperatures reached thresholds, triggering their release. Each new detection added layers to the puzzle of where and how this object formed in its alien stellar system. The mysterious nickel emissions showed particularly interesting behavior. Emission line intensity scaled steeply with decreasing solar distance, following a power law with exponent near -8 or 9. This rapid brightening suggested the release mechanism operated near a critical temperature threshold, suddenly becoming efficient as solar heating intensified. The iron lines that astronomers expected to accompany nickel remained conspicuously absent, deepening rather than resolving the chemical mystery. Visual monitoring documented changes in morphology accompanying the thermal awakening. The unusual sunward glow and anti-tail features evolved as dust production patterns shifted. Jets became more prominent in high-resolution imaging, indicating localized active regions on the rotating nucleus responding to diurnal heating cycles. The object was becoming more complex and active with every passing day. The thermal awakening had begun. Peak activity still lay weeks ahead, but already 3I Atlas displayed behavior that challenged preliminary characterizations and raised new questions about its fundamental nature. Something unexpected was happening to 3I Atlas, and astronomers were struggling to explain it. The object's brightening curve, that graph plotting luminosity against time as it approached the sun, was deviating from standard comet behavior in ways that raised uncomfortable questions. Normal comets followed predictable patterns. This visitor was writing its own rules. Conventional comet activity scaled with solar distance according to well-established relationships. Gas production rates typically followed power laws, where activity increased proportionally to heliocentric distance, raised to some negative exponent. For water-dominated comets, this exponent usually fell between -2 and -4. Carbon dioxide-rich objects showed steeper scaling, sometimes reaching -6 or 7. But 3I Atlas was exhibiting behavior that pushed beyond even these extreme values. Photometric data from early October 2025 revealed brightening rates that outpaced theoretical predictions by significant margins. The object had surged to nearly magnitude 8 in integrated brightness, making it theoretically visible to experienced observers using large binoculars under dark skies, though its proximity to the sun in Earth's sky prevented practical naked eye detection. More importantly, this brightness exceeded model forecasts based on the object's known size, distance, and previously measured activity levels. Several possible explanations existed, none entirely satisfying. The simplest interpretation suggested that initial activity estimates had been too conservative, and the object simply possessed more volatile material near its surface than preliminary observations indicated. As solar heating penetrated deeper into the nucleus, it encountered fresh reservoirs of ice that sublimated enthusiastically, boosting gas and dust production beyond early predictions. A more intriguing possibility involved outburst activity, sudden surges in comet brightness caused by discrete events rather than gradual heating. Solar system comets occasionally experienced outbursts when subsurface pressure from trapped gases built to critical levels, triggering rapid venting episodes that temporarily increased brightness by factors of 10 or more. If 3I Atlas was undergoing similar events, it would explain the deviation from smooth brightening curves. The controversial mass estimates added another layer of complexity to interpreting the activity surge. If the object truly weighed 33 billion tons, with a nucleus spanning 5 kilometers or more, the observed gas production represented only a tiny fraction of total mass. A massive body could sustain high activity levels for extended periods without depleting its volatile inventory. But if the mass estimates proved incorrect, if 3I Atlas actually resembled a more conventional 1-kilometer nucleus, then current activity levels suggested unusually volatile rich composition or unexpectedly efficient sublimation processes. Coma imaging revealed structural changes accompanying the brightness surge. New jets appeared in high-resolution photographs, suggesting fresh active regions opening on the nucleus surface as solar heating progressed. The anti-tail feature strengthened rather than fading, defying expectations that viewing geometry alone explained the phenomenon. Dust production seemed to be accelerating faster than gas emission, altering the fundamental character of the coma. The activity surge continued accelerating as perihelion approached. Whether this represented normal comet physics operating on an unusually massive object, or something more exotic, remained an open question, demanding answers that the approaching observational blackout might prevent obtaining. The molecular emissions pouring from 3I Atlas had reached extraordinary levels. Spectroscopic observations during mid-October 2025 documented gas production rates that dwarfed earlier measurements, confirming that the thermal awakening was accelerating into a full-scale eruption of volatile material. The interstellar visitor was bleeding atmosphere at a prodigious pace. Water vapor dominated the gas production budget in absolute terms, with emission rates climbing past 500 kilograms per second based on spectral line intensity measurements. This represented roughly half a ton of water escaping the nucleus every second, accumulating to over 40 metric tons per day. For context, this matched the output of moderately active solar system comets at similar distances from the Sun, though whether 3I Atlas counted as moderate or extreme depended entirely on which mass estimate one believed. Carbon dioxide contributed substantially despite water's numerical dominance. The ratio of carbon dioxide to water remained unusually high, continuing the pattern established in earlier observations. Current measurements suggested carbon dioxide production rates around 150 kilograms per second, maintaining the elevated proportion that marked this object's chemical signature. Such enrichment indicated formation in the frigid outer regions of its parent stellar system, beyond the snowline where carbon dioxide condensed efficiently alongside water ice. Carbon monoxide added another 50 kilograms per second to the volatile budget. This highly volatile species, with a sublimation temperature far below water or carbon dioxide, had been active since the object's discovery. Its production rate scaled with solar heating, just like other species, following the general trend toward explosive gas release as temperatures climbed. The exotic compounds detected in smaller quantities told fascinating stories about chemical complexity. Ammonia appeared in the spectra, contributing perhaps 10 kilograms per second. Methane emissions reached similar levels. Various organic molecules, hydroxyl radicals, and sulfur-bearing compounds added their signatures to the increasingly complex spectral fingerprint. Each detection represented a piece of the puzzle about formation conditions in alien stellar environments. Spectral line profiles provided additional information beyond simple production rates. The width of emission lines indicated gas velocities, revealing that molecules escaped the nucleus at speeds approaching 500 meters per second. These high velocities resulted from a combination of thermal motion and bulk flow patterns, as sublimating material accelerated away from the surface. The kinetic energy required to launch gas at such speeds came ultimately from solar heating, converting radiative energy into molecular motion. The nickel emissions that had puzzled researchers since their first detection showed dramatic enhancement in recent observations. Emission line intensity increased faster than most other species, following the steep power law dependence on solar distance. Production rates remained difficult to quantify precisely, but the strengthening signal confirmed that whatever process released nickel atoms into the coma was becoming dramatically more efficient. As solar heating intensified, iron lines remained absent. This persistent asymmetry, nickel without iron, continued defying simple explanations based on standard cometry chemistry. The mystery deepened as production rates surged. The gas production explosion transformed 3I Atlas from a scientifically interesting curiosity into a spectacular demonstration of volatile physics operating under extreme conditions. Peak production still lay ahead at perihelion, when sublimation rates might double or triple current values. The astronomical community was mounting the most comprehensive observation campaign ever directed at a single interstellar object. As 3I Atlas plunged toward its hidden perihelion passage, every major observatory with capability to observe the visitor was pointing instruments skyward in a coordinated effort to capture final pre-blackout data. The scale of mobilization reflected both scientific urgency and the knowledge that this opportunity would not repeat. Ground-based facilities formed the backbone of the campaign. The Gemini South Telescope in Chile dedicated substantial observing time to high-resolution imaging and spectroscopy, capturing morphological details and chemical signatures with its 8-meter aperture. The Very Large Telescope, also in Chile, contributed complementary observations across multiple wavelengths. Keck Observatory in Hawaii added its twin 10-meter telescopes to the effort whenever the visitor rose above the Pacific horizon. Dozens of smaller research telescopes at universities and private observatories worldwide filled gaps in temporal coverage. The coordination required to orchestrate this global network operated through established channels refined over years of asteroid and comet tracking. The Minor Planet Center served as the central clearinghouse for astrometric measurements, collecting positional data that fed into increasingly precise orbital solutions. spectroscopic observations flowed to specialized databases where researchers could access and analyze chemical signatures. Imaging data accumulated in digital archives that would serve future studies long after the visitor departed. Space-based assets provided perspectives unavailable from Earth's surface. The Hubble Space Telescope scheduled multiple observation sessions, using its position above atmospheric interference to capture pristine images of the developing coma structure. The James Webb Space Telescope continued its infrared surveillance, tracking the carbon dioxide envelope and searching for additional molecular species in its spectral coverage. Smaller astronomical satellites contributed where their capabilities allowed, adding to the comprehensive dataset. Amateur astronomers and small observatory networks played crucial supporting roles despite the object's challenging visibility. Photometric monitoring by experienced observers with modest equipment provided continuous brightness measurements that professional telescopes, often allocated in discrete time blocks, could not sustain. These contributions filled temporal gaps and helped characterize short-term variability in activity levels. The observation cadence intensified as superior conjunction approached. What had been nightly monitoring evolved into round-the-clock coverage as Earth's rotation carried different observatory sites into darkness. Coordinated campaigns scheduled simultaneous observations across multiple facilities, enabling comparison of data obtained under identical lighting and geometric conditions. Such synchronization proved particularly valuable for understanding how viewing angle affected apparent brightness and morphology. Radio telescopes joined the campaign despite the visitor's relatively small size, making radar detection unlikely. Several facilities attempted to bounce signals off the nucleus, hoping to determine rotation state and constrain size through echo analysis. The attempts yielded marginal detections at best, but contributed to the comprehensive characterization effort. International cooperation transcended the usual boundaries of scientific collaboration. Research teams shared data openly, recognizing that maximizing scientific return from this unique visitor required setting aside competitive instincts in favor of collective knowledge advancement. Preprint servers filled with preliminary analyses as groups rushed to extract insights before the blackout descended. The global telescope network represented humanity's collective eye turned toward a messenger from interstellar space, determined to learn everything possible before darkness fell. The spectroscopic data arriving from observatories worldwide was telling a story that grew more complex and puzzling with every observation. The chemical fingerprints embedded in light from 3I Atlas revealed not just what molecules were present, but how they behaved under increasing solar heating. And that behavior was raising questions that simple comet models struggled to answer. The water vapor emissions showed unexpected structure in their spectral line profiles. Instead of smooth, symmetric peaks that standard sublimation models predicted, the lines displayed asymmetries and occasional splitting that suggested multiple emission components. Some gas appeared to escape from discrete active regions on the nucleus, creating distinct velocity components in the spectrum. Other material seemed to arise from a more distributed source, possibly ice-rich grains sublimating after being lifted off the surface by more volatile species. The carbon dioxide signature was evolving in ways that defied straightforward interpretation. The ratio of carbon dioxide to water, already anomalously high by solar system comet standards, appeared to be increasing rather than remaining constant as both species activated more fully. This trend suggested that carbon dioxide ice was distributed differently than water throughout the nucleus, perhaps concentrated in regions that were only now becoming exposed to direct solar heating. Or perhaps the nucleus possessed layered structure with a carbon dioxide-rich mantle overlying a more water-dominated interior. Isotopic ratios extracted from high-resolution spectra added another dimension to the chemical mystery. The deuterium to hydrogen ratio in water vapor, a crucial diagnostic of formation temperature and location, showed values that fell within the range seen for solar system comets, but toward the higher end of that distribution. This supported the interpretation that 3I Atlas formed in cold outer regions of its parent system, but raised questions about whether different stellar environments produced systematically different isotopic signatures. The strengthening nickel emissions continued to baffle researchers. New observations revealed additional nickel lines across the spectrum, each showing the same steep scaling with solar distance. The emission pattern suggested nickel atoms were being released through a temperature-dependent process that accelerated dramatically as the nucleus warmed. Photodesorption, where solar ultraviolet radiation breaks chemical bonds, remained the leading candidate mechanism. But the continued absence of ion emissions made this explanation uncomfortable, since similar processes should release iron with comparable efficiency. Sulfur compounds appeared in recent spectra for the first time, with emission lines from sulfur dioxide and possibly hydrogen sulfide becoming detectable. These species required specific chemical environments to form and survive, adding constraints on the object's formation history. The detection suggested that 3I Atlas contained a richer inventory of volatile compounds than early observations indicated, with different species activating sequentially as solar heating penetrated deeper into the nucleus. Organic molecules contributed subtle features to the infrared spectra. Methanol, formaldehyde, and various hydrocarbons left their marks on the spectral signature, though at levels that challenged detection limits. Each molecule represented a tracer of chemical processes operating in the frigid disk where this visitor originally condensed from interstellar gas and dust. The spectra were screaming that 3I Atlas was far more chemically complex than any previous interstellar visitor, carrying detailed information about alien stellar chemistry. The visual appearance of 3I Atlas was undergoing dramatic transformation as solar heating reshaped its dust and gas envelope. High-resolution imaging from Hubble Space Telescope and ground-based observatories documented changes occurring on timescales of days rather than weeks, revealing dynamic processes that challenged static models of comet behavior. The mysterious sunward glow and anti-tail that had puzzled observers since July 2025 were evolving in unexpected ways, rather than fading as perihelion approached and viewing geometry changed. These features were becoming more pronounced and complex. New imaging from late October showed the forward-directed component extending further from the nucleus, creating an elongated teardrop shape that pointed almost directly at the sun. This persistent sunward orientation defied simple explanations based on viewing perspective alone. Detailed analysis of the dust distribution revealed the likely mechanism behind the unusual morphology. Large dust grains, lifted off the nucleus by gas pressure, but too massive to be swept away immediately by solar radiation, followed ballistic trajectories influenced primarily by the object's own weak gravity and solar tidal forces. These grains travelled outward initially, but then fell back or curved into complex paths that created apparent forward emission when viewed from Earth's angle. The effect resembled a fountain of material arcing away from and back toward the nucleus. Jets became increasingly prominent in high-resolution images as active regions on the rotating nucleus responded to diurnal heating cycles. At least 4 distinct jets appeared in the best images, suggesting localized areas where volatile rich material sublimated more efficiently than surrounding terrain. The jets rotated with the nucleus, which spin period measurements suggested completed 1 rotation every 12 to 15 hours. This rapid rotation helped explain the somewhat symmetric overall coma despite asymmetric surface activity. The classic anti-solar tail, pointing away from the sun as radiation pressure swept fine dust into the traditional comet tail configuration, was finally developing alongside the anomalous sunward features. Recent images showed a faint but distinct tail extending in the expected direction, creating a complex dual tail structure. The object now displayed both forward and backward directed components simultaneously, a configuration occasionally seen in solar system comets, but rarely with such prominent forward features. Color measurements across different wavelengths revealed compositional variations within the coma. Blue light scattered preferentially from the inner regions near the nucleus, where fresh dust particles recently ejected from the surface dominated the population. Red light reflected more efficiently from the outer coma, where older particles had undergone space weathering and possible organic coating that altered their optical properties. This radial color gradient provided information about particle evolution and aging processes. The dust-to-gas ratio, estimated from comparing reflected sunlight brightness with emission line intensities, appeared to be increasing as perihelion approached. More dust relative to gas suggested either that sublimation was becoming more efficient at entraining solid particles, or that ice-rich grains were fragmenting in the warming coma and contributing additional dust. Either interpretation indicated that the object's appearance would continue evolving dramatically through perihelion passage. The morphology transformation, documented in real time, showed 3-eye atlas responding dynamically to increasing solar heating, revealing internal structure and composition through observable changes in its dust and gas envelope. The question haunting every astronomer tracking 3-eye atlas had become impossible to ignore. Would this interstellar visitor survive its close encounter with the Sun intact? Or would perihelion passage tear it apart through some combination of thermal stress, tidal forces, and internal pressure buildup? The answer carried profound implications for understanding the object's true nature. History provided sobering lessons about comets that ventured too close to the Sun. The Kreutz family of sun-grazing comets, fragments of a larger parent body that shattered centuries ago, routinely disintegrated during perihelion passages that brought them within a few million kilometers of the solar surface. Some disappeared completely, vaporized by extreme heating. Others fragmented into multiple pieces that continued along similar orbits. A rare few survived intact, emerging battered but whole from their solar encounter. 3-eye atlas would pass roughly 58 million kilometers from the Sun's center, placing it well outside the Roche limit, where tidal forces alone could rip a solid body apart. The tidal stress at perihelion distance would create a gravitational gradient of only a few thousandths of a meter per second, squared across a 5-kilometer nucleus. For an object with any structural integrity whatsoever, these forces presented no threat. Tidal disruption was not the primary danger. Thermal stress posed a more serious challenge. Surface temperatures at perihelion would climb above 400 degrees Celsius, hot enough to vaporize not just water and carbon dioxide, but also more refractory materials. If the nucleus contained significant amounts of volatile ices distributed throughout its volume, rather than concentrated at the surface, internal pressure from trapped gases could build to destructive levels. Subsurface venting might create fractures that propagated through the structure, potentially splitting the object into multiple fragments. The controversial mass estimates entered the survival equation in crucial ways. If 3I Atlas truly weighed 33 billion tons, with a nucleus spanning 5 kilometers, it possessed enough gravitational self-binding to hold together against all but the most extreme internal pressures. Larger bodies could sustain higher stress before fragmenting. A massive object would almost certainly survive perihelion passage intact, though perhaps losing substantial surface material through ablation. But if the mass estimates proved incorrect, if the object actually resembled a more conventional 1 to 2 kilometer nucleus weighing billions rather than tens of billions of tons, survival became less certain. Smaller bodies possessed weaker self-gravity and more fragile structures. Historical examples of comet fragmentation occurred preferentially among smaller objects that lacked the gravitational binding to maintain cohesion under stress. Observational clues from current behavior provided some reassurance. The object showed no signs of imminent breakup, despite already experiencing significant solar heating. No secondary condensations appeared in high-resolution imaging that might indicate nascent fragmentation. The brightness evolution followed smooth trends rather than showing sudden changes that often preceded major disruption events. These factors suggested structural stability, at least under current conditions. Yet, perihelion would subject 3I Atlas to thermal environments far exceeding anything it had experienced so far. Peak heating exceeded current levels by factors of 10 or more. Internal temperatures would lag behind surface heating, creating thermal gradients that stressed the structure. Whether the visitor would emerge intact or shatter into fragments remained genuinely uncertain. The survival question would be answered definitively during the observational blackout, when human eyes could not witness the outcome. The physics of cometary breakup operated through mechanisms that astronomers understood in principle, but struggled to predict for individual objects. 3I Atlas faced multiple pathways to potential fragmentation during its perihelion passage, each involving different physical processes and producing different observational signatures. Understanding these risks required examining how thermal energy, rotational forces, and internal structure interacted under extreme conditions. Thermal fracturing represented the most immediate threat. As solar radiation heated the surface, temperature gradients developed between hot exterior layers and cold interior material. Rock and ice expanded at different rates when heated, creating mechanical stress at boundaries between different compositional zones. If these stresses exceeded the material strength holding the nucleus together, cracks would propagate through the structure. Deep fractures could split the object into multiple pieces that would slowly drift apart along slightly different trajectories. Solar system comets provided numerous examples of thermal fragmentation. Comet Schwarzmann, Wachmann 3, broke into multiple fragments during a close solar approach in 1995, eventually producing dozens of distinct pieces. Comet Linear disintegrated completely in 2000, dissolving into a cloud of debris that dispersed along its orbital path. These events occurred at solar distances comparable to or greater than 3I Atlas would experience, demonstrating that thermal stress alone could destroy cometary nuclei. Rotational instability offered another fragmentation pathway. As volatile material sublimated asymmetrically from active regions on the surface, the resulting jets created torques that could alter the object's spin state. If rotation accelerated beyond a critical threshold, centrifugal forces at the equator would exceed gravitational binding. Material would begin lifting off the surface, potentially triggering catastrophic disruption if the process ran away. The critical spin period for a 5-kilometer object with typical cometary density sat around 3 to 4 hours. Current observations suggested 3I Atlas rotated much more slowly, completing one turn every 12 to 15 hours, providing comfortable margin against rotational breakup. Internal pressure buildup posed perhaps the most insidious threat. If volatile ices were distributed throughout the interior rather than concentrated near the surface, solar heating would eventually penetrate deep enough to trigger sublimation in buried layers. Gas produced internally had to escape through porous surface material or fractures. If gas production exceeded venting capacity, pressure would build until it either found weak points to exploit or generated sufficient force to fragment the structure explosively. The structure and composition of the nucleus determined which failure mode posed greatest risk. A monolithic body of relatively uniform composition might survive thermal stress that would shatter a weakly bound rubble pile. An object with a thick insulating mantle of dust and refractory material could protect interior ices from rapid heating, reducing internal pressure risks. Conversely, a highly porous structure might allow efficient gas venting that prevented pressure buildup, but also indicated weak structural integrity, vulnerable to mechanical disruption. Observational detection of fragmentation would depend on timing and viewing geometry. Large-scale breakup into multiple kilometer-sized pieces would be obvious in any imaging. Smaller-scale crumbling might produce gradual changes in brightness and morphology that required careful analysis to distinguish from normal activity variations. The approaching blackout period meant that if fragmentation occurred near perihelion, the first clear evidence might not appear until post-perihelion recovery observations months later. The gravitational gradient across 3I Atlas during perihelion passage could be calculated with precision using well-established physics. Solar tidal forces, which varied with the inverse cube of distance from the Sun, would reach their maximum strength at closest approach. Whether these forces posed any threat to the object's structural integrity depended on comparing tidal stress against the binding forces holding the nucleus together. The mathematics began with fundamental principles. Tidal force arose because gravity weakened with distance, meaning the Sun pulled harder on the near side of 3I Atlas than on its far side. For an object with finite size, this differential created a stretching effect that tried to pull the body apart along the Sun, facing axis, while simultaneously compressing it perpendicular to that direction. The magnitude of this tidal stress scaled with object size, and inversely with the cube of solar distance. At perihelion distance of 0.39 astronomical units, approximately 58 million kilometers from the Sun's center. The tidal acceleration across a 5-kilometer nucleus amounted to roughly 0.003 meters per second squared. This represented the difference in solar gravitational pull between the object's near and far sides. For comparison, Earth's surface gravity was 9.8 meters per second squared, over 3,000 times stronger than the tidal stress 3I Atlas would experience. The Roche limit provided the critical threshold for tidal disruption. Inside this distance, tidal forces exceeded the self-gravity holding a body together, causing it to fragment regardless of structural strength. For a comet orbiting the Sun, the Roche limit sat at approximately 2 solar radii from the Sun's center, roughly 1.4 million kilometers. This was the distance where sun-grazing comets typically disintegrated when they ventured too close. 3I Atlas would pass more than 40 times farther from the Sun than the Roche limit, safely beyond any risk of pure tidal disruption. Self-gravity provided the binding force resisting tidal stress. For a spherical object with radius of 2.5 kilometers and density of 500 kilograms per cubic meter, typical of cometary material, the surface gravity amounted to roughly 0.0002 meters per second squared. This weak gravity meant that tidal forces at perihelion actually exceeded the object's self-gravity by more than an order of magnitude. This comparison seemed alarming until one recognized that self-gravity represented only one component of structural integrity. Chemical bonds, mechanical friction between grains, and tensile strength of solid material all contributed to holding the nucleus together. Even the weakest rocks possessed tensile strengths measured in millions of pascals, equivalent to supporting hundreds of meters of overburden against gravity. Tidal stress at perihelion generated pressures measured in pascals, 6 orders of magnitude weaker. The conclusion was unambiguous. Tidal forces posed essentially zero threat to 3I Atlas during perihelion passage. The object could be a loosely consolidated rubble pile held together primarily by self-gravity, and tidal stress still would not pull it apart. Any fragmentation that occurred would result from thermal processes, rotational instability, or internal pressure, not from solar tidal forces. The Sun's gravity was simply too weak at this distance to tear the visitor apart directly. The tidal force calculation eliminated one potential fragmentation mechanism, but left others very much in play. While Earth-based telescopes prepared for months of enforced blindness, one spacecraft occupied a position that would transform it into humanity's most valuable observer during the critical perihelion passage. Parker Solar Probe, designed to study the Sun's corona and solar wind from unprecedented proximity, would become the only set of human eyes capable of watching 3I Atlas during its closest approach to our star. The spacecraft carried an instrument that seemed almost prophetically designed for this unexpected mission. The Wide Field Imager for Solar Probe, known by its acronym WHISPER, consisted of 2 telescopes that captured visible light images of the solar corona and inner heliosphere. These instruments were built to observe the Sun's outer atmosphere and track solar wind structures, but they could also detect comets, asteroids, and other solar system objects that wandered into their field of view. And in late December 2025, 3I Atlas would do exactly that. Parker's orbital geometry provided the crucial advantage. The spacecraft followed a highly elliptical path that repeatedly brought it closer to the Sun than any previous human-made object, diving to within just a few million kilometers of the solar surface before swinging back out to Venus orbit. During its close approaches, Parker occupied solar system real estate that no Earth-based telescope could observe, regions hidden behind the sun's overwhelming glare from terrestrial perspective. This was precisely where 3I Atlas would be during perihelion passage. The observation opportunity would occur during Parker's 16th solar encounter, scheduled to begin in late November 2025 and continue through early January 2026. Mission planners had already modified observation sequences to ensure WSPR would capture images during the period when 3I Atlas transited through the instrument's field of view. The spacecraft would not perform any dedicated maneuvers for comet observation, but its existing trajectory placed it in ideal position for what amounted to a cosmic coincidence of extraordinary scientific value. WSPR's capabilities suited the observation challenge remarkably well. The instrument's wide field of view could capture the entire extended coma and tail structure in single images, providing context that narrow field instruments might miss. The visible light sensitivity meant that dust scattering, often the dominant source of comet brightness, would be readily detectable. Time series imaging as Parker moved along its orbit would reveal changes in activity levels and morphology occurring on timescales of hours to days. The viewing geometry offered perspectives impossible from Earth. Parker would observe 3I Atlas from angles that placed the Sun behind the spacecraft, relative to the comet, creating backlighting conditions where forward scattering by dust grains enhanced visibility. This geometry was particularly valuable for detecting faint, extended features that might be invisible in other viewing configurations. The spacecraft's motion would also provide parallax measurements that could help constrain the three-dimensional structure of the coma. Communication delays posed the only significant limitation. Parker transmitted data to Earth at relatively slow rates when far from our planet, meaning that images captured during the encounter would take days or weeks to fully download. The astronomical community would not receive real-time updates, but rather delayed reports of what happened during the observational blackout. Parker Solar Probe had become humanity's secret weapon for witnessing 3I Atlas during its moment of greatest transformation. Parker Solar Probe would not observe alone during the critical blackout period. Two additional spacecraft, designed decades earlier for entirely different purposes, would contribute their unique perspectives to the observation campaign. The Solar and Heliospheric Observatory and the Solar Terrestrial Relations Observatory, satellites, occupied positions that made them valuable secondary observers of 3I Atlas during its hidden perihelion passage. SOHO had been watching the Sun continuously since 1996 from a gravitationally stable point between Earth and our star. The spacecraft's suite of instruments included several coronagraphs, telescopes that blocked the Sun's bright disk to reveal the faint corona extending millions of kilometers into space. These coronagraphs had discovered thousands of comets over the mission's decades of operation, most of them small sun grazers that plunged to fiery destruction. 3I Atlas would pass through SOHO's field of view as it approached and departed perihelion, appearing as a moving bright spot against the background corona. The LASCO coronagraphs aboard SOHO provided different fields of view, covering regions from 1.1 to 30 solar radii from the Sun's center. 3I Atlas would transit through the C3 coronagraph's outer field of view, where the instrument's sensitivity could detect even relatively faint comets against the coronal background. Time series imaging would track the visitor's motion and brightness changes during the critical period when Earth-based telescopes saw nothing. The data quality would not match dedicated comet observations, but any information during the blackout period possessed enormous value. Stereo consisted of 2 nearly identical spacecraft launched in 2006 to observe the Sun from different vantage points. The mission originally placed one satellite ahead of Earth in its orbit and one behind, creating a stereoscopic view of solar activity. By 2025, orbital evolution had positioned the stereo spacecraft at locations that provided additional perspectives on the inner solar system distinct from Earth's viewpoint. Their coronagraphs, similar in principle to SOHO's instruments, would capture 3I Atlas from angles that complemented Parker and SOHO observations. The combined observations from these 3 spacecraft would provide something unprecedented in interstellar visitor studies. Multiple simultaneous viewpoints during perihelion passage. Parker would observe from close proximity with high spatial resolution. SOHO would track the visitor from Earth-Sun line perspective. Stereo would add observations from off-axis angles. Together, these viewpoints would enable 3-dimensional reconstruction of the coma structure and activity patterns during the peak heating phase. Coronagraph imaging imposed limitations that observers accepted as necessary compromises. The instruments sacrificed spatial resolution and photometric precision compared to dedicated astronomical telescopes. Background subtraction challenges and instrumental artifacts could complicate interpretation. Dust and debris within the instrument's fields of view sometimes created false signals, requiring careful analysis to distinguish from real comet features. Nevertheless, imperfect data during the blackout period vastly exceeded no data at all. Mission operations teams coordinated observation schedules to maximize overlap between the 3 spacecraft. While each satellite followed predetermined orbits dictating their positions, pointing directions and observation cadences could be optimized within operational constraints. The goal was ensuring continuous coverage as 3I Atlas moved through the solar exclusion zone, where Earth-based telescopes could not follow. SOHO and Stereo stood ready to fulfill roles their designers never imagined. Watching an interstellar visitor during humanity's first close observation of such an object near solar perihelion. The astronomical community faced a uniquely frustrating situation as November 2025 arrived and 3I Atlas crept closer to the Sun in Earth's sky. Every observer knew that the most scientifically valuable phase of the entire passage was about to unfold beyond their reach. The waiting game had begun, and it would test patience and resolve across the global research network. Final observations occurred under increasingly difficult conditions as solar elongation, the angular separation between the object and the Sun, shrank below 20 degrees. Observations required specialized techniques and equipment. Telescopes needed to point dangerously close to the Sun's position, risking instrument damage from stray light entering optical systems designed for nighttime use. Many facilities imposed strict safety limits, preventing observations within certain angular distances of the Sun, forcing early cessation of their monitoring campaigns. The last high-quality images arrived from observatories in early November, showing 3I Atlas at peak pre-perihelion brightness, with its complex dual tail structure fully developed. Spectroscopic observations ceased shortly afterward, as the signal-to-noise ratio degraded beyond useful levels. By mid-November, only a handful of specialized solar telescopes could still detect the visitor as a faint smudge barely distinguishable from instrumental background. Then, even these final glimpses ceased as superior conjunction rendered the object completely invisible from Earth. Research teams shifted focus from active observation to data analysis and preparation for post-perihelion recovery. The months of intensive monitoring had generated petabytes of images, spectra, and photometric measurements, requiring systematic organization and analysis. Different research groups claimed responsibility for various aspects of the dataset, working to extract maximum scientific value from the pre-perihelion observations, while the visitor remained hidden. Theoretical modeling efforts intensified during the enforced observational pause. With no new data arriving to constrain models, researchers explored parameter space more thoroughly, testing how different assumptions about nucleus composition, structure, and mass affected predictions for perihelion behavior. These models would provide frameworks for interpreting post-perihelion observations, allowing comparison between predicted and actual outcomes. Planning for recovery observations consumed significant effort. Observatories needed to schedule telescope time months in advance, requiring predictions of when 3I Atlas would emerge from solar glare at sufficient elongation for detection. The orbital solution was known precisely, but the object's brightness after perihelion remained uncertain. If substantial mass loss or fragmentation occurred, the visitor might emerge much fainter than pre-perihelion conditions suggested, necessitating deeper observations with larger telescopes. The psychological dimension of the waiting game affected researchers differently. Some welcomed the break from intensive nightly observations, using the time to catch up on other projects and recover from months of demanding schedules. Others found the inactivity frustrating, wishing for any scrap of information about what was happening in the solar exclusion zone. All recognized that the answers they sought were being written in real time by physics and chemistry operating at the sun's doorstep. But those answers would remain inaccessible until geometry permitted recovery observations. Mission teams operating Parker Solar Probe, SOHO, and Stereo prepared for their roles as humanity's only witnesses during the blackout period. Data processing pipelines were tested and refined. Communication schedules were optimized to ensure timely downlink of critical observations. Everyone understood that these spacecraft represented the only chance to glimpse 3I Atlas during its transformation. The waiting game continued as December approached and perihelion loomed. Soon the hidden drama would unfold, witnessed only by robotic eyes stationed throughout the inner solar system. December saw the 26th, 2025 marked the moment when 3I Atlas reached its closest approach to the Sun. At precisely 11 hours, 17 minutes Universal Time, the interstellar visitor passed through perihelion at a distance of 0.39 astronomical units from the solar center. Approximately 58 million kilometers separated the nucleus from the roiling surface of our star. The moment of truth had arrived, hidden from Earth's view, but unfolding according to the inexorable laws of orbital mechanics. Solar flux at this distance exceeded anything 3I Atlas had experienced during its long journey through interstellar space and into our solar system. The intensity of sunlight reached roughly 6.5 times what Earth receives, enough to raise surface temperatures well above 400 degrees Celsius on areas facing the Sun. Every square meter of the nucleus absorbed several kilowatts of radiative energy, driving sublimation rates to their maximum levels for this orbital passage. The thermal evolution during perihelion passage followed predictable patterns, even if observers could not witness them directly. As the object approached closest point, heating rates increased faster than cooling could compensate, driving surface temperatures upward. At perihelion itself, the Sun hung nearly stationary in the visitor's sky, its apparent motion slowing to almost zero as orbital velocity reached maximum but angular rate of change minimized. This created a brief period of sustained maximum heating before the object began its outbound journey. Gas production rates likely surged to values several times higher than pre-blackout measurements. Water sublimation would dominate the volatile budget in absolute terms, potentially reaching tons per second rather than hundreds of kilograms. Carbon dioxide outgassing would maintain its unusually high proportional contribution, adding perhaps several hundred kilograms per second to the atmospheric bleeding. More exotic species, including the mysterious nickel emissions and various organic compounds, would respond to peak heating with their own production surges. The morphology must have transformed dramatically during these peak heating hours. Dust production would intensify as expanding gas more efficiently entrained solid particles from the surface. The coma would expand to its maximum extent, potentially spanning millions of kilometers. The tail structure would evolve as increased dust output fed material into the anti-solar direction, while the unusual forward scattering features responded to changing viewing geometry and activity patterns. Whether fragmentation occurred remained unknown during these critical hours. If thermal stress or internal pressure exceeded structural limits, the nucleus might split into multiple pieces that would slowly separate along slightly different trajectories. Major breakup would be obvious in post-perihelion observations, but more subtle changes in activity or rotation state might indicate internal restructuring without complete disruption. The 3 spacecraft positioned to observe provided humanity's only witness to these events. Parker Solar Probe's Whisper cameras captured images from relatively close range. SOHO's coronagraphs tracked the visitor's motion across their fields of view. Stereo added observations from its off-axis perspective. But the data these spacecraft collected would not reach Earth immediately. Communication delays and downlink schedules meant that humanity would wait days or weeks to learn what the robotic observers had witnessed. The moment of truth passed in silence from Earth's perspective. Perihelion occurred, physics operated according to natural law, and 3i Atlas began its outbound journey, carrying whatever changes the solar encounter had wrought. The astronomical community would wait months to see the results with their own telescopes. The days following perihelion passage brought a peculiar form of frustration to the astronomical community. 3i Atlas had survived its closest approach to the Sun and was now moving outward along its hyperbolic trajectory. But Earth-based observers remained completely blind to its condition. The data drought continued as the visitor traveled through the solar exclusion zone, where observations remained impossible, regardless of telescope size or observer determination. Parker Solar Probe had captured images during perihelion passage, recording what happened during those critical hours when solar heating reached maximum intensity. But the spacecraft's data transmission capabilities limited how quickly those precious observations could reach Earth. Parker stored images in onboard memory and transmitted them during scheduled communication windows, when the spacecraft's position and antenna pointing permitted contact with ground stations. The downlink process operated at rates measured in kilobits per second across hundreds of millions of kilometers, turning image transfer into an exercise in patience. Initial data packets began arriving at mission control in early January 2026, tantalizing glimpses of what the spacecraft had witnessed. The first images showed 3I Atlas as a bright, elongated smudge against the darker coronal background, clearly visible but lacking the resolution needed to discern the detailed structure. Processing teams worked to calibrate and enhance these preliminary images, while additional data continued downloading over subsequent days and weeks. SOHO's coronagraphs had also captured the visitor during its perihelion passage, tracking its motion across multiple images as it traversed the instrument's field of view. These observations arrived more quickly than Parker's data, but carried their own limitations. Coronagraph images prioritized sensitivity to faint coronal features over resolution of discrete objects. 3I Atlas appeared as an extended bright feature moving against background structures, distinguishable but not sharply defined. Analysis required careful subtraction of background emissions and instrumental artifacts to isolate the actual comet signal. Stereo observations added a third perspective, but introduced similar challenges. The spacecraft's coronagraphs were optimized for solar physics rather than comet studies. Image cadence, exposure times, and wavelength coverage reflected those priorities. Still, any observations during the blackout period possessed value far exceeding their technical limitations. The data might not match dedicated comet observations from ground-based telescopes, but they represented the only direct measurements of perihelion passage conditions. Researchers analyzing the spacecraft data faced immediate questions. Did the visitor survive perihelion intact? Or did fragmentation produce multiple components? Had brightness changed in ways that indicated unusual mass loss or structural changes? Did the morphology transform as predicted, or did unexpected features appear? Each downloaded image brought partial answers while raising additional questions that could not be fully resolved without higher quality observations. The Earth-based recovery campaign remained weeks away. Current solar elongation kept 3I Atlas too close to the Sun in Earth's sky for even the most capable telescopes to detect. Predictions suggested that recovery observations might become possible in late March or early April 2026, when the object would reach sufficient angular separation for observations during twilight hours. Until then, the astronomical community depended entirely on spacecraft data trickling back from the inner solar system. The data drought was slowly ending, but the flow remained a trickle rather than the flood researchers craved. Patience remained the only option as Parker, SOHO, and Stereo gradually revealed what had happened during humanity's first observation of an interstellar visitor at solar perihelion. Perihelion passage provided the ultimate test of the controversial mass estimates that had made 3I Atlas so scientifically intriguing. The extreme heating during closest approach to the Sun would drive gas production to maximum levels, creating the strongest possible rocket effect from asymmetric outgassing. If the object truly weighed 33 billion tons with a 5-kilometer nucleus, This peak activity should produce minimal measurable acceleration. If the mass estimates were wrong, perihelion would reveal the error through post-passage trajectory changes. The physics was straightforward. Momentum conservation demanded that gas escaping from the nucleus transferred momentum to the solid body in the opposite direction. The magnitude of this rocket effect scaled directly with gas production rate and escape velocity, but inversely with nucleus mass. Double the outgassing and you doubled the acceleration. Double the mass and you halved it. At perihelion, when gas production surged to perhaps 10 times pre-passage levels, even a very massive object should show some measurable orbital perturbation if standard comet physics applied. Precise astrometry before and after perihelion would provide the critical measurements. Observers had accumulated thousands of position measurements during the pre-blackout period, establishing the visitor's trajectory with extraordinary precision. Any deviation from pure gravitational motion would appear as systematic residuals when comparing observed positions against predictions based solely on solar and planetary gravity. The size of these residuals would directly constrain the non-gravitational acceleration, which in turn would test the mass estimates when combined with gas production measurements. The test carried profound implications beyond simple mass determination. If post-perihelion observations showed acceleration consistent with a conventional 1 to 2 kilometer nucleus weighing billions of tons, it would demonstrate that the preliminary mass estimates had been dramatically wrong. The mysterious absence of measurable acceleration during pre-perihelion observations would require alternative explanations, perhaps involving unusual outgassing geometry or momentum transfer efficiency rather than extraordinary mass. Conversely, if post-perihelion astrometry confirmed minimal acceleration despite peak gas production, it would strongly support the massive object interpretation. A 5-kilometer nucleus weighing tens of billions of tons could shrug off even intense outgassing with barely detectable orbital changes. Such confirmation would force serious consideration of how interstellar debris populations differed from theoretical predictions, and why such a massive visitor appeared so early in humanity's systematic survey. The intermediate possibility deserved consideration as well. Measurable but anomalously small acceleration might indicate that 3I Atlas possessed unusual properties affecting momentum transfer between escaping gas and solid nucleus. Perhaps the outflow occurred through a distributed network of vents rather than concentrated jets, reducing thrust efficiency. Perhaps dust production was so intense that momentum carried away by dust grains exceeded gas momentum, altering the expected acceleration direction. Such complications would require sophisticated modeling to disentangle. Time would provide the answer as post-perihelion observations accumulated. Recovery astrometry needed to reach comparable precision to pre-blackout measurements, requiring months of careful position measurements from observatories worldwide. Only after sufficient data accumulated could analysts determine whether the trajectory showed systematic deviations from pure gravitational motion. The acceleration test would definitively resolve the mass controversy, but the resolution required patience as observations slowly built the necessary statistical foundation. Perihelion passage had subjected 3I Atlas to the most extreme conditions it would experience in our solar system. How the object responded to that test would reveal its true nature. April 3rd, 2026 marked a moment astronomers had been anticipating for months. The solar elongation of 3I Atlas finally exceeded 25 degrees, placing it far enough from the Sun in Earth's sky that recovery observations became possible during morning twilight. Observatories in the southern hemisphere, where autumn brought favourable viewing geometry, pointed their instruments toward the predicted position and began the search for humanity's most enigmatic interstellar visitor. The first detection came from Chile, where large aperture telescopes enjoyed dark skies and sophisticated instrumentation. Initial images showed a faint smudge at the expected coordinates, confirming that 3I Atlas had survived perihelion passage and remained detectable despite months of absence from terrestrial observations. The detection triggered immediate alerts across the global astronomical network. Recovery had been achieved. The data drought was officially ending. Those first recovery images revealed an object that appeared both familiar and transformed. The overall brightness matched pre-perihelion predictions reasonably well, suggesting that catastrophic fragmentation had not occurred. No obvious secondary components appeared in the field of view that might indicate the nucleus had split into multiple pieces. At first glance, 3I Atlas seemed to have survived its solar encounter intact, emerging battered perhaps, but fundamentally whole. Yet subtle differences were immediately apparent to experienced observers. The coma appeared more compact than pre-perihelion observations, spanning perhaps 100,000 kilometers, rather than the several hundred thousand it had reached before disappearing behind the Sun. This contraction likely reflected reduced activity levels as the object moved away from the Sun and cooling commenced. Sublimation rates decreased with increasing solar distance, following the same inverse relationship that had driven activity increases during approach. The tail structure showed notable changes from pre-blackout morphology. The dual tail configuration, with prominent sunward and anti-solar components, had simplified into a more conventional appearance. A single, relatively straight tail extended in the anti-solar direction, swept back by radiation pressure acting on dust grains. The mysterious forward scattering features and teardrop-shaped envelope that had characterized earlier observations were absent or greatly diminished. Whether this represented fundamental changes in dust production patterns or simply different viewing geometry remained unclear from initial images. Brightness measurements provided crucial early data points. Photometry from multiple observatories converged on an integrated magnitude near 9.5, roughly half a magnitude fainter than final pre-blackout observations, adjusted for current solar distance. This modest dimming could reflect decreased activity, loss of surface material during perihelion passage, or subtle changes in dust scattering properties. More observations would be needed to distinguish between these possibilities. Spectroscopic confirmation of the recovery required larger telescopes and longer exposure times. The object remained faint enough that obtaining high-quality spectra challenged even major observatories. Initial attempts detected weak emission features consistent with water vapor and possibly carbon dioxide, but signal-to-noise ratios prevented detailed chemical analysis. Plans were already underway for intensive spectroscopic campaigns. Once the visitor brightened further or better, observing conditions developed. The astronomical community exhaled collectively. 3I Atlas had survived. It had emerged from behind the Sun, damaged perhaps, changed certainly, but intact and observable. Now came the detailed analysis phase, where pre- and post-perihelion characteristics could be compared to understand what the solar encounter had revealed. The comparison between pre-perihelion and post-perihelion observations became the focus of intensive analysis as recovery data accumulated through April and May 2026. Astronomers were searching for any evidence that the extreme solar heating had fundamentally altered 3I Atlas, transforming it from the puzzling visitor that disappeared behind the sun into something observably different. The answer emerged gradually as datasets grew and analysis techniques refined the measurements. Photometric evolution showed clear changes in brightness behavior. The post-perihelion light curve, tracking brightness versus time and solar distance, displayed a shallower slope than pre-perihelion observations. Before disappearing behind the sun, brightness had been increasing rapidly as the visitor approached perihelion, following a steep power law with solar distance. After emergence, brightness decreased more gradually than the approach curve predicted. This asymmetry suggested that the object's response to solar heating had changed, possibly due to depletion of volatile ices near the surface, or development of an insulating dust mantle. The rotation state provided another diagnostic of potential changes. Light curve analysis, examining how brightness varied over hours as the nucleus rotated and different surface regions came into view, revealed a period of approximately 13 hours in post-perihelion data. Pre-perihelion measurements had suggested 12 to 15 hours, making direct comparison difficult given the uncertainty ranges. No clear evidence emerged for dramatic spin-up or spin-down that might indicate major mass redistribution or torques from asymmetric outgassing. The rotation appeared broadly consistent with pre-perihelion behavior within measurement uncertainties. Spectroscopic observations showed the most intriguing changes. The carbon dioxide to water ratio, anomalously high throughout pre-perihelion monitoring, appeared to have decreased in post-perihelion spectra. Water vapor emissions dominated more strongly relative to carbon dioxide than earlier observations suggested. This shift could indicate that surface layers enriched in carbon dioxide ice had sublimated away during peak heating, exposing underlying material with different composition. Alternatively, the thermal wave from perihelion heating might have penetrated deep enough to activate water ice reservoirs that remained dormant during the approach phase. The mysterious nickel emissions showed reduced intensity in post-recovery spectra. While still detectable, the emission lines appeared weaker relative to other species than pre-perihelion observations indicated. Whether this represented depletion of whatever nickel-bearing compounds existed near the surface, changes in the excitation mechanism releasing nickel atoms, or simply decreased overall activity levels remained uncertain. The iron lines that never appeared during pre-perihelion monitoring remained absent in post-perihelion spectra, perpetuating that chemical mystery. Morphological analysis revealed the most obvious transformation. The complex dual tail structure with prominent sunward features had simplified into conventional comet appearance. High-resolution imaging showed a relatively symmetric coma with single dust tail extending anti-sunward. The teardrop-shaped envelope and forward scattering anomalies had vanished. Whether this reflected fundamental changes in dust production patterns, depletion of the grain population creating those features, or evolution in viewing geometry as the object's trajectory carried it to different positions. Relative to Earth and Sun remained subject to interpretation. Mass loss estimates based on integrated gas production suggested 3I Atlas had shed perhaps 0.01% of its total mass during the entire solar system passage. If the 33 billion ton mass estimate was correct, this amounted to several million tons of material, substantial in absolute terms, but negligible fraction of total mass. The visitor had changed, but remained fundamentally the same puzzling object that first appeared. The definitive test of 3I Atlas's true nature came through painstaking astrometric analysis conducted throughout late spring and summer 2026. Observatories worldwide contributed position measurements as the visitor moved outward through the solar system, each observation adding another data point to the trajectory solution. The question that had haunted astronomers since the first controversial mass estimates could finally be answered with rigorous statistical confidence. Did the object's orbit show measurable non-gravitational acceleration? The analysis required extraordinary precision. Researchers compiled over 6,000 position measurements spanning from initial discovery in July 2025 through August 2026, creating the most comprehensive astrometric dataset ever assembled for an interstellar visitor. Each measurement carried its own uncertainty estimate based on observing conditions, telescope capabilities, and reduction techniques. Sophisticated orbital fitting software combined these observations into a unified solution that accounted for gravitational forces from the Sun, all major planets, and relativistic effects. The preliminary results emerged in September 2026, released through preprint servers while formal peer review continued. The fitted trajectory showed residuals consistent with pure gravitational motion within measurement uncertainties. Any non-gravitational acceleration remained below the detection threshold of approximately 8 × 10 to the negative 10th meters per second squared. This represented an improvement over pre-perihelion limits, but still found no definitive evidence for rocket effects from outgassing. The implications were profound. Gas production measurements from spectroscopy, particularly peak values estimated for perihelion passage based on spacecraft observations, suggested outflow rates that should have produced measurable acceleration if the nucleus possessed conventional comet dimensions and mass. The continued absence of detectable non-gravitational forces, even through the most active phase of the entire passage, strongly supported the massive object interpretation. Detailed modeling explored what this meant quantitatively. If gas production at perihelion reached the estimated several hundred kilograms per second, with escape velocities around 500 meters per second, the upper limit on acceleration constrained nucleus mass to exceed approximately 20 billion tons. Combined with separate constraints from activity levels and thermal modeling, the analysis converged on a mass estimate between 25 and 40 billion tons, with 33 billion representing the most probable value. This corresponded to a nucleus diameter of roughly 4.5 to 5.5 kilometers, assuming typical cometary density. The massive nucleus interpretation resolved the primary anomaly that made 3I Atlas so puzzling. An object of this size could display vigorous cometary activity while showing minimal orbital perturbation from outgassing. The physics was consistent, requiring no exotic explanations or unusual momentum transfer mechanisms. 3I Atlas was simply much larger than previous interstellar visitors, a genuine heavyweight from the space between stars. Yet this resolution created its own uncomfortable questions. Why had humanity discovered such a massive interstellar object before detecting numerous smaller specimens? Population statistics suggested this order of discovery violated expectations about size distributions in the interstellar medium. Either detection biases were more severe than recognized, smaller objects were being missed by current surveys, or theoretical models of interstellar debris populations required fundamental revision. The trajectory truth confirmed what preliminary estimates suggested. 3I Atlas was indeed a silent giant, an interstellar visitor whose mass exceeded expectations by orders of magnitude. Whether this made it typical or exceptional among objects drifting between stars remained unknown, awaiting future discoveries that might place this enigmatic visitor in proper statistical context. The perihelion passage had functioned as a natural laboratory experiment, subjecting 3I Atlas to extreme conditions that tested every hypothesis about its nature and composition. As analysis of spacecraft observations combined with pre- and post-perihelion ground-based data, a comprehensive picture emerged of what the solar encounter had revealed about this interstellar messenger. The survival itself carried significant information. Perihelion heating had subjected the nucleus to thermal stress capable of fragmenting weakly bound structures. Yet, the object emerged intact without obvious breakup. This demonstrated structural integrity sufficient to withstand temperature gradients and internal pressure buildup that destroyed less robust comets. The cohesion required to survive suggested either a monolithic body with substantial tensile strength or a rubble pile with enough self-gravity and internal friction to maintain stability under stress. Activity evolution through perihelion provided crucial constraints on volatile distribution and composition. The asymmetric brightness curve, with steeper increase during approach than decrease during departure, indicated that surface properties had changed during peak heating. The most likely explanation involved formation of a dust mantle, an insulating layer of non-volatile material left behind as ices sublimated. This refractory lag deposit would reduce heat penetration into the interior, decreasing sublimation efficiency and producing the observed brightness asymmetry. The chemical evolution documented by pre- and post-perihelion spectroscopy revealed layered composition within the nucleus. The decrease in carbon dioxide to water ratio after perihelion suggested that carbon dioxide-enriched surface layers had sublimated away, exposing underlying material with different composition. This stratification likely reflected the object's formation history, with outer layers condensing from gas with different temperature and composition than inner regions. The perihelion heating had essentially excavated through surface material to reveal deeper structure. Parker Solar Probe observations during perihelion passage captured the moment of peak activity that Earth-based telescopes missed. The WISPR images showed the coma expanding to maximum extent, spanning several million kilometers at its largest. Dust production surged visibly in time series imaging, with brightness increasing by factors of 3 to 5 during the closest approach period. The tail structure extended to unprecedented lengths, demonstrating that radiation pressure on freshly produced dust grains was efficiently sweeping material into the classic anti-solar configuration. SOHO and stereo coronagraph observations provided complementary perspectives that enabled three-dimensional reconstruction of the coma structure. The multi-viewpoint analysis revealed that the unusual forward scattering features seen in pre-perihelion observations, resulted from a combination of large grain dynamics and favourable viewing geometry. As perihelion passage altered both the dust size distribution through increased production of fine particles and the observing geometry relative to Earth, these features naturally evolved into more conventional appearance. The mysterious nickel emissions showed interesting behaviour through perihelion in spacecraft spectra. Emission intensity peaked slightly before closest approach, then decreased more rapidly than other species during the outbound phase. This suggested that whatever mechanism released nickel atoms, whether photodesorption or thermal decomposition of nickel-bearing compounds, operated most efficiently in a narrow temperature range that was exceeded during closest approach. The depletion or transformation of nickel sources near the surface would explain the weakened post-perihelion emissions. The Sun had revealed 3I Atlas to be a massive, structurally coherent object with complex internal composition and chemistry that reflected formation in environments unlike typical solar system comet birth regions. The trajectory analysis, combined with perihelion observations, delivered a verdict that resolved months of scientific debate. 3I Atlas was indeed a massive interstellar visitor, weighing between 25 and 40 billion tons, with a nucleus diameter of approximately 5 kilometers. The controversial preliminary estimates that seemed almost too extraordinary to believe had proven fundamentally correct, though refined by the comprehensive dataset spanning the entire solar system passage. Multiple independent lines of evidence converged on this conclusion. The astrometric analysis provided the most direct constraint, with upper limits on non-gravitational acceleration, requiring minimum mass exceeding 20 billion tons to explain the lack of measurable rocket effect despite vigorous outgassing. Gas production rates measured spectroscopically, particularly the peak values during perihelion captured by spacecraft observations, demanded high mass to reconcile visible activity with minimal orbital perturbation. Thermal modelling offered supporting evidence. The observed brightness evolution and thermal emission characteristics matched predictions for a nucleus with surface area corresponding to roughly 5 kilometer diameter. Smaller objects would have shown different thermal responses to solar heating, particularly different lag times between peak insolation and peak brightness. The observed behavior was consistent with a large body possessing significant thermal inertia. Photometric analysis of rotation light curves contributed additional constraints. The amplitude of brightness variations as the nucleus rotated indicated relatively modest elongation or surface heterogeneity. This was consistent with a large spheroidal body where shape variations represented smaller fractional deviations from mean radius. Highly elongated objects or small irregular bodies would produce larger amplitude light curves than observations showed. The statistical significance of the mass determination reached high confidence levels. Formal error analysis, incorporating all measurement uncertainties and systematic effects, yielded a most probable mass of 33 billion tons, with uncertainty range of plus or minus 7 billion tons at 95% confidence. This represented a factor of 3 to 10 times more massive than 2I Borisov, and potentially thousands of times more massive than Oumuamua, making 3I Atlas by far the largest confirmed interstellar visitor. The verdict carried immediate implications for understanding interstellar object populations. If objects of this size existed in the galactic debris field and could reach the inner solar system where detection became possible. Population models needed revision. Current theories struggle to explain how such massive objects got ejected from their parent stellar systems efficiently. Planet-to-planet scattering typically launched smaller debris more easily. Stellar flybys provided more plausible mechanisms for ejecting massive objects, but required specific geometric conditions. The size distribution problem remained unresolved. Detecting a 5-kilometer object before finding numerous smaller specimens violated naive expectations about how interstellar surveys should progress. Either detection biases favored large active objects more than models predicted, or the true population contained relatively more massive objects than theoretical frameworks suggested. The Vera Rubin Observatory would soon begin operations with sensitivity to detect interstellar visitors at unprecedented rates. Within years, statistical samples would replace speculation about whether 3I Atlas represented typical or exceptional visitor mass. The mass estimate verdict transformed 3I Atlas from a puzzling anomaly into a confirmed heavyweight, the first massive interstellar visitor humanity had detected and characterized. Whether it would remain the largest or simply represented the first of many such giants would be determined by future surveys, discovering what else wandered through the space between stars. Perihelion passage had activated volatile species that remained dormant or weakly active during the approach phase, revealing chemical complexity that transformed understanding of where and how 3I Atlas formed. The complete volatile inventory, assembled from spectroscopic observations, spanning the entire passage, painted a portrait of an object born in environments profoundly different from inner solar system conditions. The water ice that dominated gas production in absolute terms showed isotopic signatures distinct from typical solar system comets. Deuterium to hydrogen ratios measured from high-resolution spectra fell at the enriched end of the distribution seen in Kuiper belt objects and Oort cloud comets. This heavy isotope enrichment indicated formation at very low temperatures, where deuterium preferentially incorporated into water molecules. The signature pointed to birth in the frigid outer regions of the parent stellar system, possibly beyond 50 astronomical units from its sun. Carbon dioxide enrichment relative to water remained the most striking chemical peculiarity. Even after perihelion passage altered the ratio through preferential carbon dioxide depletion from surface layers, the proportion exceeded values seen in all but the most carbon dioxide-rich solar system comets. This extreme enrichment required formation beyond the carbon dioxide snowline, where temperatures dropped below -125 degrees Celsius. Such conditions existed only in the distant reaches of protoplanetary disks, where giant planet formation might occur. Nitrogen chemistry revealed through detection of ammonia and molecular nitrogen provided additional formation constraints. The ammonia to water ratio suggested condensation temperatures in the 50 to 70 Kelvin range, consistent with formation in trans-Neptunian analog regions of the parent system. Nitrogen isotope ratios, though measured with lower precision than deuterium, hinted at values distinct from solar system norms. This could indicate different stellar metallicity or nucleosynthetic history in the birth environment. Organic molecule detections expanded dramatically as perihelion heating activated previously dormant species. Methanol appeared strongly in post-perihelion spectra after being barely detectable earlier. Formaldehyde acetylene, and various other simple organics contributed emission features across infrared wavelengths. Complex organic compounds likely existed as well, though their spectral signatures overlapped, making individual identification challenging. This organic richness suggested that 3I Atlas formed from material that underwent significant chemical processing in a dense molecular cloud environment before incorporation into its parent protoplanetary disk. The sulfur chemistry provided unexpected complexity. Sulfur dioxide and hydrogen sulfide both appeared in spectra, with abundance ratios suggesting oxidized sulfur dominated over reduced forms. This oxidation state carried information about oxygen availability and chemical conditions during formation. The sulfur inventory might have originated from sulfur-bearing ices or from mineral phases that decomposed during perihelion heating. The nickel emissions that had puzzled observers throughout the passage showed correlation with organic molecule detections in post-perihelion spectra. This association suggested that nickel might be bound in organometallic compounds, rather than existing as pure metal or simple mineral phases. Such compounds could form in dense molecular clouds through gas phase chemistry or grain surface reactions. Their presence in 3I Atlas indicated that the object retained pristine material from the earliest phases of its stellar system's formation. The chemistry revolution, documented by perihelion observations, revealed 3I Atlas as a chemical time capsule, preserving information about conditions in an alien stellar system billions of years ago. The volatile inventory reflected formation in cold outer regions, where complex chemistry operated under conditions Earth-based laboratories struggled to replicate. The successful perihelion passage and confirmed massive nature of 3I Atlas transformed the Juno spacecraft redirection proposal from speculative possibility into urgent decision requiring immediate action. The Jupiter encounter opportunity, scheduled for March 16, 2027, was approaching, and mission planners needed months of preparation time to execute the complex orbital maneuvers required for intercept. The window for deciding was closing rapidly. Post-perihelion data had resolved key uncertainties that affected mission planning. The visitor's trajectory was now known with extreme precision from comprehensive astrometry spanning over a year of observations. The object had survived perihelion intact, eliminating concerns about intercepting a dispersed debris field rather than a coherent nucleus. The confirmed 5-kilometer size made it a substantial target, less likely to be missed if navigation errors occurred. Every piece of new information strengthened the scientific case for attempting close encounter. The engineering analysis had progressed significantly since initial proposals circulated in late 2025. Mission designers had refined the trajectory solutions, identifying optimal dates for initiating orbital maneuvers that would redirect Juno from its current Jupiter science orbit onto an intercept path. The calculations required using Jupiter's gravity through carefully timed engine burns to modify Juno's trajectory efficiently. The Oberth effect, where propulsive maneuvers performed at high velocity near Jupiter yielded maximum trajectory change per unit fuel, made this approach feasible within available propellant margins. Fuel inventory represented the primary constraint. Juno carried limited hydrazine reserves for attitude control and orbital adjustments. Redirecting toward 3I Atlas would consume essentially all remaining propellant, ending any possibility of returning to Jupiter science operations. the mission would become a one-way ticket to interstellar visitor, encounter, trading, guaranteed planetary science for uncertain but potentially revolutionary comet investigation. Congressional interest had evolved from supportive letters into active pressure for mission approval. Multiple representatives cited the unique opportunity and public interest in humanity's first close encounter with an interstellar visitor. Some argued that the confirmed massive nature made the science case overwhelming, justifying the sacrifice of remaining Juno-Jupiter observations. Others emphasized the decades that might pass before another suitable opportunity arose. NASA leadership faced competing pressures and genuine scientific trade-offs. The Juno extended mission was producing valuable data about Jupiter's interior structure, magnetic field evolution, and atmospheric dynamics. Each orbit added incremental knowledge to ongoing investigations. Terminating these observations prematurely would disappoint the planetary science community and abandon guaranteed results for uncertain gains from comet encounter. The timeline added urgency to deliberations. If NASA approved the redirection, maneuver planning and spacecraft commanding needed to begin immediately to meet the March 2027 encounter window. Delaying the decision past October 2026 would likely make the mission impossible due to insufficient time for proper preparation and testing of command sequences. Mission managers needed answers within weeks, not months. International partners expressed interest in contributing to encounter operations if the mission proceeded. European Space Agency scientists proposed coordinating ground-based observations to complement spacecraft data. Japanese researchers offered expertise in comet science and data analysis. The mission had evolved from American solo effort into potential international collaboration, reflecting global fascination with 3I Atlas. The Juno dilemma intensified as the decision deadline approached. Approving redirection meant abandoning proven science for revolutionary but uncertain outcomes. Declining meant watching the best spacecraft encounter opportunity pass unused, perhaps forever. The political dimension of the Juno decision escalated throughout October 2026 as congressional representatives intensified their advocacy for mission redirection. What began as polite letters of inquiry evolved into formal hearings and public statements, pressing NASA to seize what politicians characterized as a once-in-a-generation opportunity. The scientific decision was becoming entangled with political considerations that extended beyond pure technical merit. Multiple congressional committees claimed jurisdiction over the decision. The House Science Committee scheduled hearings to examine the costs and benefits of redirecting Juno versus maintaining its Jupiter mission. The Senate Appropriations Subcommittee controlling NASA funding indicated that approval or denial of the redirection could influence future budget allocations. The political machinery was engaging with unusual intensity for what was technically a mission operations decision normally left to agency discretion. Public opinion played a significant role in motivating congressional interest. 3I Atlas had captured popular imagination in ways that typical astronomical discoveries rarely achieved. The mysterious massive visitor from interstellar space, with its unusual chemistry and confirmed survival through solar perihelion, generated media coverage that transcended specialized science outlets. Opinion polling showed strong public support for attempting spacecraft encounter, with majorities favoring redirection even when informed about the trade-offs against continued Jupiter science. The economic arguments entered congressional discourse alongside scientific considerations. Proponents emphasized that Juno represented a sunk cost, with the spacecraft already built and operating. Redirecting it toward 3I Atlas would extract additional value from existing assets, rather than requiring new mission funding. The incremental cost of encounter operations would be modest compared to developing and launching a dedicated interstellar visitor mission. This framing appealed to budget-conscious legislators seeking maximum return on space exploration investments. Critics within the scientific community pushed back against political pressure, arguing that mission decisions should follow established peer review processes rather than congressional mandate. Planetary scientists noted that Juno continued producing groundbreaking results about Jupiter's interior and magnetosphere. Terminating observations prematurely would create gaps in datasets that required temporal continuity to maximize scientific value. Some researchers questioned whether political enthusiasm should override careful cost-benefit analysis by experts best qualified to evaluate competing priorities. The international dimension added complexity to congressional considerations. If NASA declined to redirect Juno, would other space agencies pursue their own interstellar visitor missions and potentially gain scientific leadership in this emerging field? Some legislators framed the decision as competition for scientific prestige and technological demonstration. Allowing the opportunity to pass might signal declining American commitment to bold space exploration initiatives. NASA administrators found themselves navigating treacherous political terrain. Approving redirection without strong internal scientific consensus risked alienating the planetary science community. Declining to redirect, despite congressional pressure, could trigger budget retaliation or loss of institutional autonomy in future mission decisions. The agency needed to balance scientific merit, political reality, and institutional interests while facing aggressive deadlines that prevented extended deliberation. The congressional pressure reflected genuine public fascination with 3I Atlas, but also created dynamics that complicated rational decision-making. Mission choices that should have been driven primarily by scientific merit were being influenced by political calculations and media attention. The dilemma illustrated broader tensions between democratic responsiveness to public interest and expert-driven technical decision processes. The pressure continued building as the October deadline for final decision approached. NASA would soon need to announce whether humanity would attempt its first close encounter with an interstellar visitor. While the Juno decision consumed immediate attention, mission planners worldwide were developing alternative concepts for encountering interstellar visitors, either as backup options if Juno redirection failed, or as frameworks for future opportunities. The engineering studies revealed both the challenges and possibilities of humanity, mounting dedicated intercept missions to objects passing through our solar system. The European Space Agency commissioned preliminary studies for a rapid response mission architecture capable of reaching interstellar visitors within months of discovery. The concept relied on keeping a spacecraft in ready status, pre-fueled and integrated, that could launch on short notice when suitable targets appeared. Propulsion requirements dominated the design, with chemical rockets proving inadequate for the high velocity changes needed to match trajectories with hyperbolic visitors. Ion drives offered better performance, but required years of thrusting unsuitable for rapid response. The studies concluded that existing technology could enable encounters only if targets were discovered early in their approach, providing sufficient lead time for rendezvous trajectory planning. Solar sail concepts attracted renewed interest as potential low-cost options for interstellar visitor missions. A spacecraft using sunlight for propulsion could achieve high velocities without carrying propellant mass, theoretically enabling intercepts that conventional rockets could not accomplish. However, sail deployment and control posed significant engineering challenges. The technology remained largely unproven for deep space applications, despite successful demonstrations in Earth orbit. Development timelines measured in decades made solar sails unsuitable for near-term opportunities, like 3I Atlas, but potentially valuable for future visitors. Nuclear propulsion emerged in concept studies as the most capable but politically challenging option. A spacecraft powered by nuclear thermal or nuclear electric engines could generate thrust far exceeding chemical systems, enabling intercepts with minimal advance warning. Several design concepts showed technical feasibility for reaching interstellar visitors within weeks of detection from Earth orbit. However, regulatory hurdles and public acceptance issues surrounding nuclear spacecraft complicated implementation. No space agency had launched nuclear-powered deep space missions in decades, despite theoretical advantages. Private sector entities proposed commercial mission concepts, trading government decision timelines for entrepreneurial agility. Several aerospace companies outlined privately funded missions that could launch on commercial rockets within months of target identification. The business models remained uncertain, relying on a combination of scientific data sales, media rights, and philanthropic funding. Whether commercial space could realistically mount interstellar visitor missions without government partnership remained to be proven. The Breakthrough Starshot initiative, originally focused on interstellar probe concepts, pivoted to examine how their laser propulsion technology might enable solar system interstellar visitor intercepts. Directed energy beaming could theoretically accelerate small probes to extreme velocities, reaching targets conventional propulsion could not match. However, the technology existed only in preliminary laboratory demonstrations. Practical implementation required advances in laser power, beam control, and spacecraft miniaturization, unlikely to materialize within relevant timescales. International collaboration offered potential pathways around individual agency constraints. A joint mission pooling resources and expertise from multiple space agencies could distribute costs and risks while combining complementary capabilities. Coordination challenges and competing national interests complicated such partnerships, but the scientific value of interstellar visitor encounters might justify the diplomatic effort required. All alternative concepts shared common recognition that 3I Atlas represented a preview of future opportunities. The Vera Rubin Observatory would soon discover interstellar visitors at rates of dozens per year. Developing responsive mission architectures now would position humanity to capitalize on this coming flood of targets. Whether Juno redirected or not, the engineering groundwork laid during 2026 would enable future encounters with messengers from between the stars. The comprehensive study of 3I Atlas from discovery through post-perihelion recovery had transformed understanding across multiple domains of astronomy and planetary science. The visitor's passage through our solar system delivered lessons that would shape how humanity approached interstellar objects for generations to come, regardless of whether spacecraft ever achieved close encounter. The most fundamental lesson concerned interstellar object diversity. Previous visitors, Oumuamua and 2I Borisov, had suggested a simple picture where interstellar comets resembled solar system analogues, while more exotic objects remained rare anomalies. 3I Atlas shattered this comforting assumption by demonstrating that massive visitors with unusual chemistry could appear early in systematic surveys. The sample size of 3 remained statistically meaningless, but the range of properties already observed indicated that interstellar space contained far more diversity than preliminary observations suggested. Population statistics received a wake-up call from the visitors' confirmed mass. Theoretical models predicting size distributions in the interstellar medium needed revision to accommodate how humanity discovered a 5-kilometer object before detecting numerous smaller specimens. Either ejection mechanisms operated differently than models assumed. Survival rates during interstellar transit favored larger objects more than anticipated, or detection biases were more severe than recognized. Resolving these questions would require larger samples from next-generation surveys. Chemical analysis techniques advanced significantly through the intensive spectroscopic campaigns. The unusual carbon dioxide enrichment and mysterious nickel emissions. Without iron pushed observers to refine methods for extracting compositional information from faint spectra. The isotopic measurements, though challenging at the distance and brightness levels involved, demonstrated feasibility for characterizing formation conditions in alien stellar systems. Future visitors would benefit from improved calibration and analysis procedures developed for 3I Atlas. Astrometric precision reached new heights through the global coordination of position measurements. The techniques refined during trajectory monitoring, combining thousands of observations from hundreds of observatories into unified solutions, established protocols for future interstellar visitor tracking. The ability to detect non-gravitational accelerations at the level of billionths of a meter per second squared represented a quantum leap in capability that would enable subtle dynamical studies of future objects. Multi-asset observation coordination proved its value during the perihelion blackout period. The combination of Parker Solar Probe, SOHO, and stereo observations, despite limitations of instruments designed for solar physics rather than comet studies, demonstrated how creative use of existing space-based assets could overcome observational challenges. Future mission planning would incorporate lessons about viewing geometry and instrument capabilities learned during 3I Atlas monitoring. Thermal modeling of activity evolution through perihelion passage improved understanding of how volatile sublimation responded to extreme heating. The asymmetric brightness curve and chemical changes documented before and after closest approach provided empirical constraints on models of surface processes and internal structure. These observations would inform predictions for how future visitors might behave during close solar encounters. The survival through perihelion demonstrated that even relatively fragile cometary material could withstand substantial thermal stress if possessed sufficient size and structural integrity. This reduced concerns about whether future interstellar visitors might disintegrate before detailed study became possible. The resilience gave confidence that objects detected early enough in their approach could be tracked through complete solar system passages. Perhaps the deepest lesson involved humility about what remained unknown. Every answer 3I Atlas provided raised additional questions about interstellar debris populations, planetary system formation, and chemical evolution throughout the galaxy. The visitor served as a reminder that the universe continued surprising humanity despite centuries of astronomical observation. The infrastructure developed to study 3I Atlas was transforming into permanent capability that would revolutionize how humanity detected and characterized future interstellar visitors. The lessons learned, protocols established, and coordination networks built during 2025 and 2026 would ensure that the next messenger from between the stars received immediate comprehensive attention from a prepared global community. The Vera Rubin Observatory represented the most significant upgrade to detection capabilities. Beginning full operations in 2027, the facility would scan the entire southern sky every few nights with unprecedented depth and cadence. Simulations predicted discovery rates of 50 to 100 interstellar objects annually once the survey reached full operational tempo. This flood of detections would transform interstellar visitor studies from curiosity-driven investigation of rare events into statistical science with meaningful sample sizes. Automated alert systems refined during 3I Atlas monitoring would immediately flag potential interstellar candidates based on orbital characteristics. Within hours of discovery, follow-up networks spanning multiple continents would begin confirmation observations and preliminary characterization. The days or weeks that passed between Oumuamua's discovery and comprehensive follow-up would not repeat. Future visitors would receive coordinated attention from the moment automated surveys identified them. Spectroscopic response capabilities had matured significantly. Major observatories maintained target of opportunity programs specifically designed for rapid response to transient phenomena, including interstellar visitors. Chemical characterization that required weeks to arrange for 3I Atlas would occur within days for future objects. The spectroscopic databases and analysis tools developed during the Atlas campaigns would enable immediate comparison with previous visitors, quickly identifying whether new objects showed similar or distinct chemical signatures. Space-based assets were being positioned with interstellar visitor observation as explicit secondary mission objectives. The James Webb Space Telescope had demonstrated its value for infrared characterization during 3I Atlas monitoring. Future scheduling would prioritize rapid response to new discoveries. Parker Solar Probe's successful perihelion observations of 3I Atlas established precedent for using solar physics spacecraft for comet studies when geometry permitted. Mission planners would watch for future opportunities. International coordination frameworks established during Atlas monitoring created institutional memory and communication channels that would activate automatically for future visitors. The Minor Planet Center's role as central clearinghouse for astrometric data was now explicitly extended to interstellar objects. Spectroscopic and photometric databases maintained by professional and amateur networks had refined submission and quality control procedures. The theoretical framework for interpreting observations had expanded dramatically. Models relating activity levels to nucleus properties, chemical signatures to formation conditions, and dynamical behavior to physical characteristics had been tested against real data from 3I Atlas. Predictions for future visitors would start from empirically validated baselines, rather than untested assumptions. The surprise factor that made Oumuamua so puzzling and 3I Atlas so challenging would diminish as theoretical understanding caught up with observational capability. Mission concepts for spacecraft encounters had progressed from speculation to detailed engineering studies. If suitable targets appeared with sufficient advance warning, rapid response missions could launch within the technology and budget constraints of existing space agencies. The Juno decision, whether ultimately approved or declined, had forced detailed examination of what spacecraft encounters required and what they could achieve. Most importantly, the astronomical community had developed collective expertise in interstellar visitor studies. Researchers who cut their teeth analyzing 3I Atlas data would form the core of teams studying future objects. The learning curve for each new discovery would be less steep. Standard analysis procedures would replace improvised responses. The next interstellar visitor would still bring surprises, guaranteed by the diversity already apparent from 3 examples. But it would not catch humanity unprepared or uncertain about how to respond. 3I Atlas had taught astronomers how to study messengers from between the stars. 3I Atlas continued its outbound journey through late 2026 and into 2027, gradually fading from view as distance from both Sun and Earth increased. The interstellar visitor that had captivated astronomical attention for over a year was returning to the darkness between stars, carrying with it information about our solar system, just as it had brought chemical signatures from its alien birthplace. Observations became increasingly challenging as the object dimmed below magnitude 15 in November 2026. Only the largest telescopes could still detect it against the background stars. Final spectroscopic measurements occurred in December, capturing faint emission lines that confirmed water and carbon dioxide remained active despite the growing distance from solar heating. By January 2027, 3I Atlas had faded beyond the practical detection limits of most facilities. The trajectory carried it back toward interstellar space, along a path that would take millions of years to reach even the nearest stellar systems. The visitor had gained velocity during its solar system passage, accelerated by the Sun's gravity as it fell inward, then climbed back out. This gravitational slingshot effect left 3I Atlas traveling slightly faster, relative to the local standard of rest, than when it arrived, a tiny energy exchange between our Sun and the interstellar medium. The departure marked an ending, but also a beginning. Everything learned from studying this massive visitor would inform humanity's approach to future interstellar objects. The techniques refined, the coordination established, and the questions raised would shape astronomical research for decades. 3I Atlas had served as both teacher and mystery, resolving some puzzles while creating others. As the silent giant faded into the cosmic distance, astronomers were already preparing for the next visitor. The Vera Rubin Observatory was beginning operations. New detection systems were coming online. The flood of interstellar discoveries was about to begin. 3I Atlas would not remain alone for long in humanity's catalogue of visitors from between the stars. But it would always hold the distinction of being the first massive interstellar object humanity studied comprehensively, the silent giant that forced us to recognize how much remained unknown about the space between stellar systems.